All right. So, hey, Justine, welcome. At the end of class today, remember to have me mark you tardy instead of absent. Okay. So, the test is this week. It will cover everything that we've learned so far, one-dimensional and two-dimensional motion. The big pieces of it are going to be conceptual problems in nature, like what happens if I do this? Not the ones that are like a car is going 45 meters per second and decelerates. At this rate, what's the stopping? It's not going to be a lot like plugging numbers in, okay? So it'll be about 8 to 10 multiple choice and 2 to 3 free response questions. And so what might a free response question look like? I'm so glad you asked. Okay, so a free response question might look like this. Here is my table. This should look familiar. The ball rolls off the table and it hits the ground. Draw your velocity versus velocity in the x direction, velocity in the y direction, acceleration in the x, and acceleration in the y graphs versus time. Is that something you want to do to practice so that you know it? Good, then you might want to start like writing that out on a piece of paper or on a tablet. This would be a good writing time. And Brandon, I am recording this, and so I'll put it up online. So if you get tired and want to go to bed, I'll put it in the place too.
Yeah.
Yeah.
Okay. I'll stay. It's not too late.
No, because you're like in Cambodia or something. Where are you?
No, I'm so it's like 9:46 p.m. I'll be fine.
That's not even my bedtime yet.
Yeah, exactly.
Dubai. Okay. Yeah. Guys, I don't know that I've ever had a class of just boys before. It's really weird. Huh? Mm-hmm. Yeah, she left the class. She decided that she just didn't want to spend that much time with me. It's just the way it goes. It's not that she didn't love physics. It's just, you know. I won't. Okay. I think I've given you enough time. Does somebody want to tell me what one of the graphs would look like? Any one of these. A straight line? Really? The velocity in the x direction? Is it moving in the x direction? So will the velocity in the x direction be 0? It'll be positive and constant. Okay. Somebody want to give me another graph? A? Acceleration in the x direction. Okay, Mufu, you got this. Straight horizontal line on 0, because is this accelerating in the x direction? No, sirs. All right. Somebody else give me another graph. VY, what does that look like? It's what? Straight down. I don't like it. Like, to me, this is straight down. Diagonal, good. It's hard to describe the shapes. I get it. Okay, so this is the velocity. That guy with his mower. Every day. So the velocity in the y direction, there is no initial velocity in the y direction because it's not being shot up or down. And so it starts at 0, but it travels in the downward direction or the negative direction. Always assume that this direction is positive and up is positive, unless you're told otherwise. So what's the last graph going to look like? Straight line, horizontal, negative. And if you had to put a number here, what number would you put? Negative 10. Makes sense to me, right? This is meters per second squared. That looks fabulous. This would be an okay free response question, but would probably be leveled up. We'd probably level it up a bit, such that I say, oh, I have this guy and I have this guy. How would their graphs of these things compare? Vy is the same. It's going to be like what? Oh, yeah. Oh, perfect, yeah. So it's going to be right on the axis because it's not moving in the x direction, right? Are your acceleration graphs any different if I shoot it horizontally? No, I haven't changed anything about the horizontal motion or like the acceleration. Nothing's pushing or pulling it, so these are going to remain the same. What could you say about, anything else that you could say about this scenario? What about the position?
What do you mean you can say about
Well, I don't know. Anything else that you would know about this? I have 2 balls, one's shot and one's dropped. Anything else like of note for these 2 balls? It's a weird open-ended question. They're in the air at the same time. Right? They're in the air the same amount of time. If I were to take another ball and drop it, shoot it with twice the velocity, how does that change the time in the air? Not at all. Why not at all? Yeah, the horizontal velocity doesn't tell you anything about the time in the air. If I were shooting it upwards, that would be different. How could I change the time that it's in the air? I could make it taller. That would change the time in the air. Okay, so the red one is also the same time in the air. How would that change my graphs?
that'll get the Vx of the black one
Twice as high. So if this is V, this is 2V, it'll be here. But these guys are all going to be the same. Okay, that's a good question. That's a really nice long free response question. There's a lot of good stuff in there. What would the motion map, the dot diagram, does anybody need this still? You're good? What would the motion diagram or the motion map look like for these? Let's just go back to the green and the black. So this guy is just moving in 1 dimension, but this one's moving in 2. So we're going to have to take that into account with our motion diagram. Why don't you go ahead and take a minute to draw your motion maps. Remember, those start with dots. So I'm going to start my green one here. Oh. That's not the marker I was just using. There we go. So this guy is going to be drawn in 2 dimensions because it's moving in 2 dimensions. The black one will be drawn in 2 dimensions, its motion map. What will the motion diagram of the ball that's dropped look like? The gap between the points will... Say it again. Yeah, the gap between the points will increase because the dots are equal increments of time, and as time goes on, the distance between them gets bigger and bigger because it's going faster and faster, so it's covering more and more distance in the same amount of time. What would the black ball's position versus time graph look like? This guy. Not position, sorry. Motion map. My brain. Yeah, what would its dot diagram, its motion map look like? Two-dimensional. Good.
So each dots are going to be the same height.
They're going to be in the same height. So this guy is going to be a height here, and this guy is going to be at height here, and this one here. Cool. I like the way you're saying. I like what you're saying here. Yeah, where would it go horizontally along this line? The intervals would be equal. And so if this guy is here, then it's the same equal interval. So it's going to be here, the same equal interval, here, same equal interval, here, same equal interval, maybe here. So notice how this is a curved, I didn't do a great job, a curved line. Where the distance horizontally doesn't change from dot to dot as time goes on. It's not linear though, right? It's not like that. It's not a straight line, it's a curved line. Yeah. Because if you were to think about it, it's following this path. So it's going to have to be dotted along this path somewhere, along this curved path. Okay. Questions over this? It's like crickets. All right. My next question is basically just the, let's go with no, we'll keep this. The discussion question that you guys did, I think it was Brandon, had like a really great explanation, well thought out in that discussion. I'm going to keep those dots. They'll come in handy later. I have two balls. One starts at the bottom, and I throw it up, and it reaches some height h, and then it comes back down. And then the other ball starts at height h. Ooh, let's make this a different color. The other ball starts at height h, is dropped, and travels downwards. Where will they intersect in the air? Halfway? Less than half? Or more than half? More than half? Why do you say more than half? This. Yep, this one's being thrown up. And this one's being dropped. So it's sort of like that-ish. That's not a great, but this one reaches this height at this one, like the height at which this one is dropped, but it's at the same time. Ryan says upper half. Anybody have any other thoughts? less than half? Where would they meet each other in space? If you did it on the same vertical, like where would they hit? Would be a good thing, but where would they, at what point are they going to pass each other? More than half? More than half? Less than half? Anybody want to give me a good reason? Good explanation? So good. So Ryan says if I draw my position versus time graph, one that's dropped looks like this. Fabulous, right? The one that's thrown upwards looks like this. And so just by that, Ryan's like, this is more than half. And then this second half here will look exactly like this piece. That's a really good way to reason your way and a very nice explanation. Anybody have a different explanation for why it's going to be more than half?
Because in the upper half it has lower velocity, so in a certain amount of time, both travels further distance, a lot of half than the upper half.
Good. This one starts off slow. So in the same amount of time, if it starts off slow, even if their acceleration is the same, it starts off slow. This one starts off fast. So while this one is speeding up and this one is slowing down, this one already has a fast initial velocity, meaning that it will cover more distance in the same amount of time. That's fabulous. That's exactly where you were going with that, I think. Any other ways that you could think about this? For me, like this motion diagram is like my super epic best friend. So this is the motion diagram for something that's dropped, right? It goes and it gets faster and faster and faster. Okay. What would the motion diagram look like for the one that's thrown up in the air? The same, because it starts off fast, right? Starts off with a big velocity, and then its velocity gets smaller and smaller and smaller over time. And then it looks like that one on the way back down, right? And so you can use this motion map just like you have used them in the past with your two fingers. Two fingers. One is getting thrown and the other one is being dropped. And then sometime later it's here and here. Then here and here. Then maybe here and here. And so that looks like more than half to me. That was a bug. Okay? Questions? I feel like such a great teacher when there are no questions, or like a really terrible teacher. Yeah. Yeah. Yes. So Brandon, the question is, if this was a free response question, could you just explain it via the motion maps? Yeah, I would say that that's fairly acceptable. I would always go back to like, how do you know the motion map looks like this? And so I would write down the change in position is the initial velocity times time plus 1/2 acceleration times time squared. Because of this equation, as time goes, the change in position will get bigger for this guy. And so its motion map will look like this. So I would not necessarily use the equation to do anything other than root the explanation of what I'm showing you, that you know that I'm right because this equation. Yeah, you could absolutely plug in random numbers to solve it. Absolutely. Yep.
So that's why they're going to add more than half.
Yeah. Yeah, so yeah, you can use the basic ideas. You can use this equation, velocity initial plus acceleration times time, talking about how the acceleration is the same, right? The acceleration will be the same, the time is the same, and so the change in velocity for the two will be the same. And then if this one starts at a high velocity, well, then it will have a greater, like, average velocity. I don't know. You could, yeah. But yeah, you can explain it like that. Yeah. Root it in, root your explanation in fact and evidence. And it doesn't have to be super, like, crazy. Just like Ryan was like, I drew the position versus time graphs. Like, if you draw your position versus time graphs like this, just make sure that you explain why they're drawn like that. Like, that's fine. One's fast and slowing down, and the other one's slow and speeding up. That's fabulous. Good explanation. Anything else?
I have a question.
Yeah, Brandon.
So is the final velocity of the green ball the same as I guess, like, is the final speed of the green ball when it touches the ground the same as the speed of the black ball when it's being thrown up?
Yes. Brandon's question is, so is the final velocity of the green ball going to be the same as the initial velocity, but magnitudes, right? Going to be the same as this as it's thrown? Yes, it is. Because they reach the same height in the air. They have the same height. And so you could prove that to yourself saying the final velocity squared is the initial velocity squared plus 2 acceleration change in position. If their change in position is the same and their acceleration is the same, and this one, the final velocity is 0, this one, the initial velocity is 0, meaning the other term has to be the same. Absolutely, Brandon. Yes. Any other questions? More than half, yep. And we could probably work out what that more than half is. I would assume that there's going to be some weird square root function of something in there. So
Yep.
We're not going to do that. Don't worry about that. That's too much. Okay.
So on the test, would you provide the drawings for the questions, or is it our job to figure out?
Some of them I'll like if it's a ball rolls off of a table, I'll probably give you a table and a ball. I might provide the drawings on some of them, but not every one of them.
Because, like, on the discussion question, like, I didn't know what you meant by less than half, not half, and more than half. I was kind of thought it backwards.
Oh, yeah.
So I thought less than half would be where it is,
I will try to be better explainer. But yeah, this one I probably would have had a picture like this so that you were on board. I just didn't get the picture in the discussion.
Am I going to know on campus what is the test going to be on paper?
Yes, it's going to be a paper test. I can't make a online test. That is just too much. Yeah, it's going to be
Class or, like, outside?
in class next Thursday in class. And so we'll be in the classroom because taking a test on a chair without a table is not great. That stinks. Yeah. Other questions?
What about us?
Oh, what about you? I'm still thinking, Brandon, but I feel like it will be a PDF copy of the test that is emailed to you.
Okay.
And then you can answer it and then scan it. You'll have a certain amount of time to give it back to me. And depending on when the class meets, I might make you, like, log in just so that I can see that you're not, like, I don't know, working with a professor to solve. I don't know. I might make you face like video chat as you're taking it.
Oh, that's too much.
Yeah.
It's
I
good.
haven't gotten that far. Test integrity. I pretty much trust you guys, but like, trust but verify, right?
Yeah.
Trust
mhm.
but verify. But it will be a PDF that I email to you at the time that you want it. Also, like if we don't have class in the morning, you can be like, I want to take it at 10 o'clock at night, Virginia time, and I will email it to you, and then you'll have like 2 hours to get it back to me. Hour and a half
Okay.
from when
Got
I
it.
send it.
Mhm.
And if you want it at 4 in the morning, I can pre-program my email to send it at 4 in the morning.
I'll be joining the class anyways.
Oh, okay, cool. And you can use the equation sheet that's on the topics page, also on the bulletin board. If you are in this week's topic, it's like the first thing, and there's a couple of notes, and then there's an equation sheet. There's a Calvin and Hobbes comic on it. You can print that out and bring it. Okay. One more question before we just go into work time. And I'm happy to answer any questions that you have that have come up. So my next question, and this was my favorite example. This is just one-dimensional motion, but this is one of my favorite questions. You're standing on a cliff, and you have two balls. One, you throw upwards with some velocity v, and it goes up, and it comes back down. The other one, you don't drop it. You don't drop it. You throw it. You throw this one downwards with the velocity of negative v. And then it hits the ground. Compare the final velocities, or the velocity at the ground, between the two balls.
So you throw one upward.
Yep.
And you drop the other one.
You don't drop it, you throw it downward.
Alright.
Yep. This one gets thrown upward and this one gets thrown downward. I'm not recognizing your answer, but I am going to let somebody else voice an answer before I start saying things. Okay. The crickets on this side of the room make me think that you guys did not watch this sweet video that I made, huh? They're the same? Why are they the same, Nick? Yes. And so now, do you see any difference between the ball here and the green ball? No, they have the same initial downward velocity now. And so they will hit the ground with the same final velocity. What's the velocity of the ball at the top of its motion? Good. Other questions? Yeah. What would the acceleration for the green ball be? After it's thrown, what's pulling on it? So the acceleration is going to be, yep, opposite G. The throwing doesn't count. Yeah, so with everything that we're doing, it's the motion after you give it the motion. So it's like I throw it, I only care about what happens once it leaves my hand. Yeah, that's a good question. Just like when it hits the ground, I only care about the fraction of a second before it hits the ground. Obviously, the ground will stop it. We don't care about that right now. Mufu. Why do I say opposite G instead of negative? Yeah, so G, what does G stand for? No, try it one more time.
Acceleration due to gravity.
It is this, so AG is the acceleration due to gravity. That's weird, I know. G is something else. So close. Justine said gravitation. Gravitational pull. Basically, yes. G is the gravitational field strength. Little g is the gravitational field strength. It is a positive number. Little g is a positive number. This will come into play later, not later, next week, when we start talking about forces, because the force of gravity is the same thing as what word? Anybody? Weight, good. Which is m times g. It's not mass times the acceleration due to gravity, it's mass times the gravitational field strength. So this is an important distinction, that G is just a number. It's not positive or negative. I made a YouTube video about that too. It's on my new YouTube channel, so like and subscribe. It's a good YouTube channel. As of last night, 0, but I'm really hoping to hit how many kids do I teach? About 45. I'm really hoping to hit about 45 in the next couple of weeks.
So, Dr. P, some of what you said, the final velocity of those two objects, the ball, are going the same. Because regardless, when they hit the end, that's when the acceleration and the velocity will be the same.
So, the final velocities when they hit the ground will be the same, yes. And my explanation, they have the same acceleration, you're right, but that's for the whole time. That even includes the time that this one's going up. Their acceleration will be the same. This one goes up with a velocity of v. The velocity becomes 0. It turns around, its velocity increases, and when it reaches the same height, its velocity is now negative v, which is the same as this one is. So now from here, the problem is the same. Same distance, same velocity, same time. Yeah, that's a good question.
What if we apply air resistance?
What if you apply air resistance? It would probably change, but I don't know how it would change. Yeah, I don't know. That's a good question. We're not going to do that. That's too much. But if that's something that you're super interested in, Justine, send me an email and I will dig in. Okay, I'll dig in. Yeah. Because air resistance is weird because it's not linear. It goes as velocity squared. And so...
What if it's when you throw the ball and it's raining, there's a storm going on?
Yeah, that's so many extra. Justine is asking what happens if it's raining and there's a storm happening and the balls are getting whipped around. What would happen then? That's so much, Justine. I don't think I've ever done that problem in my entire life, and I have a PhD in physics. I do. I shouldn't. I feel I should not call myself a doctor. You are right. Okay. Any other questions that you have?
Is air resistance just a common number like gravity?
It is. Is air resistance a common number like gravity? No, because it depends on the density of your air, right? So the air resistance is some constant v squared. Gives you the force of air resistance. Yeah, and this constant depends on what your air pressure is, what your density is, how much water vapor is in the air. Yeah, it's super tricky. It's super tricky. All right. Any other questions? Let me see that I hit all of the high points that I wanted to hit. That and that. There's going to be lots of graphs. So like understanding graphs, understanding position versus time graphs and velocity versus time graphs. What does the slope mean? What does the area mean? How do you know on a velocity versus time graph is something turning around? How about a position versus time graph? And then there was a like problem set that was a bunch of questions, and the first one or one of them that it contained was like a toy truck being shot off of a table. Those questions, my friends, are gold. Those questions are gold. They are gold. They are just such good questions, aren't they? They're from last week, and it was a bunch of questions. Some of them were ranking questions, but they had a picture of like a truck, like a toy truck that was being rolled off of a table. Those are fabulous questions. But your AP, the AP classroom questions are also very good questions. The multiple choice from last week, very good questions. So there's a lot of good questions to choose from.
So for the resources, like, do you recommend us to watch the videos on the topic page again?
Good question. Let me see what I wrote on this week's topic page. Hold on. Like and subscribe to my YouTube channel. That's the most important. I recommend going back through the content in the previous topics section. Watch the videos, take notes, rework the problems. Don't focus on the math problems, focus on understanding the concepts. I can read too, Justine.
It's a rhetorical question.
Oh, okay.
Ask the rhetorical
Oh, it was a rhetorical question. I see. I see now. Yes. Yes. I don't mean to like throw super shade. But I mean, you know, if I'm gonna throw shade at Mufu for not like being on the topic section and like watching the videos, I'm gonna throw shade at anybody else too. I can't just pick on Mufu all the time. Or James. All right. So at this point we have what, like over a half an hour. We have a half an hour left in class today, which is you going back through stuff. I think that I have made it available that you can look at definitely all of the quizzes, like assessments from last week. I went in, and if you got something wrong, I put in nice comments like why your answer was wrong, what you should be thinking about. You should have access to all of those like answers, questions, and stuff. 3-4 was having some troubles earlier, so I put the questions and answers for that in the general section of the teams. Just a couple of pictures in the general section of teams for 3.4. So I've given you feedback on everything that you've turned in, I think.
Where do I get access?
So if you go into like your assessments, you can go back through and look at all of the stuff you've turned in. It should be blue and you should be able to click on it. And if you can't, let me know and I will see what I can do about that. I haven't gone back to all of them, but definitely the ones from last week are there. All right, any other questions right now? Half an hour. You should be studying. You should be asking me questions. You should be working on things. If you need a table, you can come up here for a table. If you need a more comfortable chair, you can go to this Adirondack chair. If you're going to move, put your mask on.